Hello everyone. Today we'll be talking about Chapter 4, Perfect Guess. Okay, before I begin, I'd just like to say that for this term, there are total four chapters, right? Chapters 2, 3, 4, and 5. The two main chapters are 4 and 5, okay? Perfect Guess and STEAM. But chapters 2 and 3 are the supporting modules, okay? Because for this term, you have STEAM and Perfect Guess. Okay, the idea of 2 and 3, right, is to support you with the fundamental knowledge before you can approach solving their problems. What kind of fundamental knowledge are we talking about here? If you have gone through chapters 2 and 3, you will know that you need to know what are the properties of your fluid, okay? What kind of fluids? Fluids in your system. Okay, either open or closed system, you have fluids like water, gas, oil, things like that. So what's important is the properties within the system. What kind of properties are we looking at? Properties like pressure, volume, temperature, enthalpy, internal energy, mass, density, so on and so forth. Okay, so as you go at a certain configuration of the properties, right, it gives you a state. So at a certain pressure, at a certain volume, at a certain temperature, you have one state. Okay, and when this fluid go from one state to the next, okay, it is something like from one point to the next point. Okay, the line joining the 2 points is called a process. Okay, so the key idea between chapters 4 and 5 is that either be it a perfect gas or steam, we will always be talking about a thermodynamic process that goes from initial to final, or from the inlet to outlet, and what goes on during this single process. Okay, is it work done, is it heat transfer, things like that. Okay, and in order to know this, on top of the properties, we also talk about the first law of thermodynamics. Okay, by using the first law and what you'll be learning in chapters 4 and 5, you will be able to find all the properties in the beginning and the final state, and all the work done and heat transfer during the whole process. Okay, so this is the idea of chapter 4, 2, 3, 4, and 5. Okay, so for perfect gas, okay, it's also called an ideal gas. Okay, by the word ideal, it means that it is not real, it is imaginary. So it is basically a theoretical gas that the scientists come up with to try and hypothesize how a real gas will behave. Okay, so take for example, you have on your first page of perfect gas, okay, page 52, you have already some examples of the gases here, of the real gases: carbon dioxide, oxygen, hydrogen, or even air. Alright, so what we know is that if the air is an ideal, if the gas is an ideal gas, it will follow this equation, okay, whereby P is pressure, and the unit has to be in pascals. Okay, in order for this formula to work, this equation to work, you need all these units to be in pascals. Volume will be meter cube. Okay, mass, of course, in kilogram. Temperature is in Kelvin. Okay, it is not in degrees Celsius, it is in Kelvin. The difference is between degrees Celsius and Kelvin is 273. Okay, as you can see from the notes. Oh, sorry, it should be Kelvin is 273 plus degrees Celsius. Okay, and this R is the unique one, because this R is called what we call the gas constant. It is a constant value, but for a different gas, it will have a different value. So for air, it is 278. kilojoule per kilogram, no sorry, 287 joules per kilogram Kelvin. Okay, if you look at other gases like carbon dioxide, okay, you actually see that carbon dioxide has a value of 189 and hydrogen has quite high, 4124. Okay, so depending on what gas you're talking about, you use a different gas constant here, but this gas constant will not change as your temperature or volume or pressure changes, so it is a constant. Okay, if we say that this gas behaves ideally, this equation is true. Okay, and you can with this you can calculate for the unknowns that are inside your questions. Okay, also with this, what we can say is if the gas goes from state one state to the next, of initial state to the final state, you can somehow shift this equation around. For example, P1 V1 at state 1, mass will not change, okay, during the whole process. R will not change, and T1 is the initial state. So what we can do is we can actually shift PVT to the left side. What you get is this. Okay, and the right side is actually MR. And we know that MR does not change at any moment over here from 1 to 2. Okay, we can also write this P2V2 equals to MR T2 for state 2. Okay, you can also see that P2V2 over T2 is also equals to MR. Okay, so in that case, right, we can form an equation between state 1 and state 2. P1 V1 over T1 is actually equals to P2 V2 over T2. Okay, so with this, a lot of this is the basis, okay, of what comes out from the perfect gas characteristic equation. So these two equations applies no matter which kind of process you are looking at. Okay, we have 5 main processes. Later we will talk more about this, but what we are saying here is that no matter which process is it, these two equations will not go wrong. Okay, if we are talking about ideal gas, okay, don't be mixed up with steam. Okay, steam has a totally different treatment, and steam will not have this perfect gas characteristic equation. So let's say we go to example 4-1. Okay, the gas is in a vessel of 1.5 meter cube. So that is your volume. So your volume is already here, 0.5 meter cube. And the pressure is already given to you. Pressure is 1.2 bar. Okay, to convert from bar to Pascal, it is times 10 to the power of 5. And it has a temperature of 25 degrees Celsius. Okay, if we want to convert to Kelvin, it is 25 plus 273. It will give you 298 Kelvin. So my volume, pressure, and temperature are all here with their respective SI units. And it's given that your gas constant R is 175 joules per kilogram Kelvin. Please note that R must also be in SI unit. Okay, a lot of times this you will be given to you. Okay, so you need to multiply by 1000 in order to get your unit to be J per kgK. Okay, so what is the mass? So PV equals to MRT. Mass, you put one side, R and T you shift over, PV over RT. Okay, and you put everything in SI units. 10 to the power of 5 times 1.5 over 175 times 298. Okay, you get 3.45 kilogram. Let me check. Yeah. So part 2 is so this gas now has a new volume, 2.1 meter cube. Okay, and the temperature is 323 Kelvin. Okay, so what is the pressure now? Okay, we can use this PVT concept. P1 V1 T1 equals to P2 V2 T2, right? So this is actually V2 and T2. These are actually P1, V1 and T1. Okay, so I can just chuck everything inside. 1.2 times 10 to the power 5, 1.5, 298. Pressure, I don't know. 2.1323. Alright? And the pressure is okay, so my pressure is 92905 Pascal, okay, which is 0.929 bars. Okay, so this is how we can make use of the characteristic equation, and P1 V1 over T1 equals to P2 V2 over T2.